In this video, I'm going to show how you can teach density using children's wooden blocks. For this activity, I'm going to use numerous rectangular prisms that are made out of wood, and I have some triangular prisms as well, a scale to get their mass, and a ruler. I'm going to use the ruler to measure the length, width, and height of my objects. Now, to keep track of them, I've labeled each one with, so I can record them in my data table. Okay, I'm going to start with A, the largest one, and I'm going to measure the length, which we can see here is 8 centimeters, the width, which is 4 centimeters, and the height, which is 4 centimeters. So I'm going to record that in the data table, and I'm going to record the measurements for all of my objects. Here is my data table that shows the volume that was calculated from measuring the length, width, and height of each of the prisms. And what we can see is that block A is twice as big as block B. And we see that A, and here's B, and it's twice as big. We see that block B is twice as big as block C. You can see that here. B is twice as big as block D, this way, and B is also twice as big as block F, because it's a triangular prism. You can see that it's twice as big. So when we measure the mass, we see that B is a little bit more than half as much as block A. When we take the mass and divide it by volume and get density, they're close. When we look at the mass of blocks C, D, E, and F, we see that they're pretty much half the mass of block B, but yet the density is roughly the same, because the mass over volume gives us density. So if we take half the mass and we get half the volume, then we're going to get the same density. Because density doesn't depend on the size of the object, it depends on what the object is. So since these are all made out of the same type of wood, they're all going to have the same density. And that's what we see for the rest of the blocks as well. So we got, for all of the blocks that I measured, we got an average density of 0.62. Okay, next I'm going to graph the data. Since I know that our data is positive, then we're going to work in the first quadrant. And since the mass of the prism depends on the volume of the prism, the mass is our dependent variable. It'll go along our y-axis. And the volume is our independent variable, and that'll go along the x-axis. And here is my graph of the data. And we can see that it appears to follow in a straight line. So there's a very strong correlation between the mass of the prism and the volume of the prism. Okay, there's a couple of places, like here when the volume is 32, that we have several data points, because we had several prisms that had the same volume and slightly different masses. So when we go to draw this in, since the volume of the prism, when it's 0, the mass of the prism should be 0, then we know it's a direct variation, and it's going to go through the point 0, 0. So when I place my ruler down here, I'm going to go through 0, 0, and place it so that it is close to as many data points as possible. I drew in the blue line for the prisms that connected many of the data points going through the point 0, 0. And now what I want to do is to find the slope of this trend line. So I'm going to look to see where the trend line crosses at the corner of the boxes on my graph, where the value for the x and the y would be integers. And at the point I labeled A is 1, and point B, so from point A I can count up 3 spaces, which is actually 6 units for the mass of the prisms, and across I count over 5 spaces, which is 10 cubic centimeters, so I get the change is 6 over 10, which is 0.6, so I get that to be the density, or the average density of my trend line, which is very close to the 0.62 that I got on the average value. And then on the calculator I got the slope of my A, or the slope of the line is A, which is 0.59, B is 0.75, and my R value, or the strength of the correlation, is 0.997. So it's a very strong correlation. And the A, the slope of the linear regression, is very, very close to what I got the other 2 ways. What I also see is B is the y-intercept, or where it crosses the y-axis, and we can see that even though it should be 0, 0, it's not quite. It's a little bit less than 1, because that's a little bit of the error in the calculations that I have when I actually measured it. Okay, now we also see, we know that the mass of 1 cubic centimeter of water should be 1. And when we draw that in, where the mass of, or the density of water being 1, that's this line right here. That's the slope of 1. So we see that our graph is less than 1. The slope of our line is less than 1, which means that the density of our blocks is less than 1, so it should float in water. And let's see. Okay. Here's my container of water, and I'm going to place in the little tiny cube, and we can see that that floated. I'll try a bigger cube, and you can see that that floats. Try the long rectangular prism, and we see that that floats as well, because it doesn't matter the shape, because each one of those has a density less than 1, and water has a density of 1, then they're going to float. It doesn't matter the shape. What matters is their density. And that concludes our video on density. Thank you.